Do you need to complete the square? You could, but you don't need to. How would you find your zeros on that problem? Factor. What times what's 6? You add together to get 5. 2 and 3. Okay? And that gives you zeros at x equals -2 and -3. Now, the zeros of a function are where they cross which axis? The x-axis. So I know that this being a parabola, a positive x squared, which way are my tails pointing? Remember our awesome dance moves from yesterday, right, Mackie? Yeah, he's embarrassing to watch it. But, so we know our tails are up. I know that my zeros cross at -2, -3. So it has to do something like this. Okay. Now, the idea of using those rules for what's happening at the tails for graphing, it allows you with any polynomial to know what's happening at the very ends. Now, to get to see what's going on in the middles, it kind of deals with where your zeros occur, and the idea that when you have a second-degree polynomial, how many terms can you have up to in the actual polynomial? Second-degree polynomial means it's an x squared, x, and a constant. So how many terms can you have? 3 of them. So when you're talking about the number of terms in a polynomial, it'll always be n plus 1. What I mean by n, whatever your nth degree is. Okay? Whenever you're talking about a polynomial about how many zeros it can have, it'll be the number up to n. So in this case, I could have up to 2 possible zeros. Now, the other thing that happens then, you have what's called a change of direction. In a parabola, how many changes of directions are there? 1. It goes down and up, which means you're going to have n minus 1 changes of direction. Now, what's going to happen eventually, we have n, so this is nth degree polynomial. We'll have n plus 1 terms in the polynomial. N possible zeros, and minus 1 possible, let's see, now, I say possible changes in direction. It does happen from time to time if you have like x to the 4th plus 9. You're just going to see what would look like a parabola. There isn't those extra changes in direction. Little things like that. But what we're trying to get at today is look at how we can go to a polynomial, figure out what's happening at the tails, and see if we can come up with a way of figuring out where it crosses the x-axis without too much of a hassle. Okay. A couple of things that we're going to be able to do with that. Well, we can make up some quick tables, just substitute in -2, -1, 0, 1, and 2, see where things are bouncing around on the axis, see where things go, and go from there. Now, what I wanted to show you back up here, the reason that we do what's called that synthetic division or synthetic substitution is that if you knew what a possible zero was, and you substitute that in to the polynomial that you're given, if you go through the process, watch what happens. What do I get for my last term? A 0. When that happens, that means the value that you just divided by is a 0 of the polynomial. So if -2 is the 0, what's its term? No, if -2 is the 0, what's its term? In parentheses, remember? X plus 2. that's the idea that I kept telling you guys when we were factoring the different. We pay close attention to the idea between zeros and terms. Zeros can go backwards to give you a term. Terms can go and give you a zero. So, it is, and we normally don't show that method until it gets to the crappy looking. And we're going to build towards that. So we're going to build towards that. So what I want to then, excuse me, if we look at, I want to look at this polynomial. And I want to look at the end behavior, and I want to kind of do a rough sketch of what it looks like. And we're going to use our tables in our calculator because it's a little bit easier to do instead of trying to make everything super crazy. So we have f of x is x cubed plus x squared minus 4x minus 1. That would be considered a third-degree polynomial. It has 4 terms to it. It can have up to how many changes in direction? 2. Okay? And that's just by going by the term, or the nth degree, excuse me. What are your tails dancing as? Which one is it, Matthew? The thing. Which the thing? Which thing? It's down, up? Okay. So our tails are down, up. I know that at the very end, it's going to be a down, up. And when I say down, up, that means I'm going from left to right. You guys figured that out by now, right? So if it's up, up, I would say up to up, up to down, down, down. It's like I'm waving in an airliner. Good times. So throw this in your calculator. Oh, wait. It was what, x squared or x cubed? I look at the graph. There's always going to be a couple of decent values that you'll be able to find out. For example, if I'm looking at this, what's the constant of the polynomial represent? What's the constant of the polynomial represent? Think about it. What is the constant of this? What does that constant represent? What is it? Oh, constant, the number at the end. The y-intercept. The -1, yes. Sorry, I didn't realize you weren't up on the vocabulary of that word constant. Sorry. So, yes. It's mathal. Wait, vocabulary, mathal. Anyway, so our constant, our digit at the end, the one without a variable, represents the y-intercept. So we know that the y-intercept, ooh, jeez. We know the y-intercept does that. We know our tails are down and our tails are up. What goes on in the middle is dependent upon what the table says. So what we do is we just look for a couple of points that are clean. What I mean by that is I would probably graph stuff around like negative. Oh, see what happens between -2 and -1? See how it stays constant at 3? But what happens in between those 2 points, you think? It changes direction in there, right? Because it's going back down. So if you go back and look at the graph, we know that something happened between at 3. So if I put in just the y equals 3, between -2 and -1, it stayed at 3, but on the graph, it actually goes up above it. So that point above that would be technically called a localized maximum. It's not a maximum of this function because since the tails are constant, is there ever a maximum? Is there ever a minimum? No. There's never a maximum or minimum for one of these because no matter what, your tails are down up. Same thing if it was up down, there'd be no maximum, no minimum. But you could get minimums with parabolas and things like that. So what we call this value here, we call that a localized maximum. What you can do with the calculator is you can still calculate maximum. You can still hit second, calculate maximum. And what we want to do is just go to the right and the left of that value. Gives me a localized maximum at that order pair. And a lot of times these order pairs are crap. That's fine. No big deal. And then you can do the same exact thing for a localized minimum. Does that make sense about looking at those? So basically what we're doing, we're just kind of looking at the calculator really for a lot of this to kind of give us an idea of where the things are changing direction. It's a third degree polynomial. See how it changes direction twice. That's a good. All right. More often than not, your odd numbered exponent ones will always have the n minus 1 change directions. Sometimes your quadratic style, the fourth degree, or your even ones, sometimes depending upon how the polynomial is written, you might not have, if it's an 8th degree polynomial, you might only have 1 change. It's completely possible. That's why we say possible. That's why we say possible zeros and things like that. So we do something like that. There it goes. Along its variable way. I don't think it's perfect, but whatever. Close enough. Oh, that's the wrong one. I think I really need to do much more, do I? Yeah, it was literally the end of 6.2. I thought I had more of them. I really didn't have more of them. All right. Apparently 6.2 is a lot shorter than I thought it was. Well, we didn't do all of it. What's that? How do you make your graph like that? It's, all right, if you look at it, you've got 1, 2, 3 changes of direction. What's that? Well, it's not going to be this one, because see how it's negative, how your tails would be down, down. This one would probably be B. Yeah, it would have to be 49. And that's the idea by looking at your tails of understanding. Well, it wouldn't be because your tails are up, so it has to be. Well, the only one that has 2 tails up is that. That's the only one that does. And that's what I mean by you have a 6th degree polynomial, but it doesn't necessarily mean you're going to have 5 changes of direction. It doesn't necessarily mean you're going to have 6 possible zeros. So let's do this. On 6.2, I might as well just give you a little bit of time to do that. Let's do the 35, that's 37, 45 odds. And let's add in what we have right now. We'll do a couple more synthetic things because that's really good practice. 334. And then No, I just found out that I still have people missing. So, in that last group here, I just want you to graph me the tails. Okay? I want to graph me the tails. I don't want to actually get through and graph these yet. The tails. I want graphs of the tails because until we get to the point of understanding how do we generate possible zeros where things occur, how do we generate all that, there's no reason for us to go back and forth into the calculator and the table to get all these crummy numbers when in fact in about a week we're going to figure out a way that's really clean. Okay. Yeah, just do your tail dance. So you can just plot your two arrows, whichever way they're going, and do that stuff, okay? Let us do that for now. I mean, I could do 6-3, but we might as well do 6-3, 6-4 tomorrow. Yeah, but how did it break? I think I still have it on the. Can I put it on the calendar for? I think it's 16 Mondays too. But it doesn't get any value mentioned in there. Yeah, anytime your calculator gives you like an invalid dimension or invalid domain values and whatnot, a lot of times the easy way to fix that is to just do a hard reset. And the way we do, remember how we do the hard reset on those? Second plus 712, second plus 722. It's good times. Has that gotten fast by the time you did a couple of them? Isn't it nice? It's a super awesome, easy way to factor stuff. Second plus 712. If you do the 712 first and then 722 restores all the details. The 712 wipes everything out, and then 22 puts it back to like your 10 by 10. Sometimes we go the opposite, like less stuff up on it.
Yeah. Like, I love sitting there. And, like, I never, like, I talked to you in the morning, and I never talked to him. And that was, like, one thing, and I think he's funny, so. Oh, research? Yeah. We don't like it. Favor put me right in front. Right in front. She knows outside. And how all my freshmen teachers, everyone.
When it says, don't pay attention to what they say to describe the end behavior like they do in the book. The way that that's written says, as y goes to something, x goes to something. Nobody talks about y. I'd rather you guys just pay attention to what the tail is. Just go ahead. Yeah, anytime that you're using synthetic division, if it's missing a value, always put a zero, whether even if it's the constant.